energy. Number 12, this is about electrolysis of brine. This topic has been taken up from the AS syllabus, so you won't be asked this at all anymore. But I can tell you that we do keep something away from the chlorine product that you will get at the anode, because this is concentrated. This is concentrated NaCl from your O-level, GCSE level, or IGCSE level chemistry. You have Na plus, OH minus, Cl minus, and H plus. Well, the NaCl from the salt, the brines, and then OH minus and H plus. But you have concentrated NaCl from the salt solution, from the brine, the seawater. You're going to discharge Cl minus and H plus. H plus is cation, goes to the cathode. Reduction happen at the cathode. So you get reduction of H plus, giving you hydrogen gas at the cathode. But the Cl minus, the anode, is going to give you CO2 gas as a result of the loss of electrons, oxidation at the anode as a result of reduction at the cathode. If you produce chlorine at the anode and we are left behind with this NaOH, so our solution become more and more alkaline. Cl2 plus NaOH can undergo this thing which is still in your syllabus. It's called disproportionation. This can happen at room temperature, mean in cold conditions, and this gives you your classic mild disproportionation. Chlorine 0, chlorine minus 1, chlorine plus 1 there, because it's sodium plus 1, oxygen minus 2, so chlorine must be plus 1 oxidation number there. Balancing the equation, you get 2 NaOH, and you can see the Cl0. Cl0 get both oxidized as well as reduced in the same reaction. This is a very special redox reaction. It's called disproportionation, where one species is both oxidized and also reduced in the same reaction. Of course, if you heat up, if the reaction gets heated up, then you can go to the more extreme disproportionation, where you will not stop at chlorine plus 1. Instead, you will stop at chlorine plus 5. That will be NaClO3. It's called sodium chloride V, or sodium chloride 5. So you need to keep the chlorine separated away from the NaOH product to prevent this side reaction called disproportionation there. Number 13, we have this group 2 chemistry. So these are mixtures. Each one behave as a mixture of 2 carbonate compounds. You can use them as fire retardants because they decompose in the heat, giving you CO2. And we know that CO2 is used to help to put out fire, does not support combustion. Okay. So what happened is what is the order of effectiveness as fire retardant from the best to the worst? From the best means it will decompose easily. So the easier you are to decompose, the easier it is to get the CO2, therefore can put out fire better. So this is about the thermal stability of the group 2 carbonate. Down the group 2, as the radius of the cation increases, you're going to become less and less polarizing. If you think about this thing called charge density, so this is charge density of the cations. Since the anion is carbonate, they are all the same. The charge is the same because they are all group 2 ions, but the size is different. The size, or I can say volume, charge over volume is basically charge density. So your size increases down group 2 as a result of more electron shells being filled. Therefore, your charge density of cation will decrease. And when your charge density of cation decrease, they become less polarizing on the CO3 2 minus ion. So this will be covered more in the A2 thermal stability essay for the group 2 carbonate. So the M2 plus cation become less polarizing on the CO3 2 minus. Therefore, it becomes harder to decompose the carbonate. In terms of the stability, the thermal stability will increase down group 2. What we have here is barium carbonate. Am I correct? Barium carbonate as well as calcium carbonate. So 2 there. And then the next one we have calcium carbonate and magnesium carbonate. And then the next one we have magnesium carbonate and we have calcium carbonate. But I think we have this unusual species here. We got like 3 of them. It's just the way they are mixed. But the idea is the one which can decompose easily into CO2 will be for the magnesium carbonate, followed by calcium carbonate, which is below magnesium, and then barium carbonate. If you have more of the magnesium carbonate, they can decompose easier. okay, because they contain magnesium, which has smaller cations, more polarizing on the anion, easier to decompose. The hardest one to decompose, the worst one, the worst effectiveness, because they don't decompose easily, is going to be something that has barium carbonate. So barytoxide is going to be the worst one. So A and C is out. The best one is going to be the one that contain a lot more magnesium carbonate, because this is the easiest to decompose, and therefore it's going to produce a larger amount of CO2, and they can smother or they can stop the fire from spreading, because it can be used to extinguish the fire. So the huntite is going to be the best fire retardant material there. So option D is going to be the only answer there. In this next question, we have this silicon chloride, so the chloride of period 3 elements, and we are doing hydrolysis. Since we are reacting it in the presence of water, we will see the presence of, or not just presence, but the emergence or the appearance of a white insoluble solid, as this is a silicon dioxide is insoluble in water. So it will be a white solid, insoluble white solid. And together with that, we will also generate some steamy white film, which is the HCl. Balancing our equation will come out with 2 H2O there and 4 HCl. So this comes as a gas. So there's a liquid at room temperature and pressure, and they will get hydrolyzed. This reaction is called hydrolysis. Very, very exothermic reaction, as you are forming a giant covalent structure with a lot of strong covalent bond there. So there is a steamy white film, which is a result of the exothermicity of this reaction, and it generates out a large amount of HCl gas as well. So what we get is a steamy white film, HCl, and we get a white precipitate, the insoluble silicon dioxide, which is why SiO2 is just insoluble water, it's just not acidic at all, not basic, it's just pH 7 water as a result of its non-solubility there. So option B is the best answer. Question 15. We have these atomic radii for these elements, magnesium, aluminium, silicon, and fluorine. These are consecutive elements across a period, and this is period number 3. Even without looking at the periodic table, as an A-level student, you're supposed to know that the atomic radii decreases across a period from sodium all the way to chlorine, and then argon in your periodic table, not periodic table actually, in the data booklet, the argon will have a much bigger atomic radii than sodium. So we just look and focus from sodium all the way to chlorine, but here in particular we're just looking at magnesium all the way to phosphorus, and they will decrease. So if we look at atomic radius, which is on the y-axis, so we know that in terms of the atomic radius, so we will have magnesium being the biggest, and then followed by aluminium, followed by silicon, followed by phosphorus. This is in terms of atomic radius on the y-axis. So we look at this, the highest is magnesium, the biggest in size is magnesium, the smallest is phosphorus. We can see that the phosphorus is not the smallest there, and therefore B is not the answer. The phosphorus is the smallest, that one is fine there. The phosphorus is the smallest, that one is also fine there. Okay, but then D, the phosphorus is also smaller, so that one is also fine there. At least I've crossed out option B there. Okay, that is in terms of atomic radius, atomic radii there. Now, in terms of melting point on the x-axis, of course, the melting point graph that we are more used to has the melting point on the y-axis, so that is what I'm going to draw first. The metals increases in their melting point as the metallic bonding increases in the strength, and then silicon all the way at the very top because of the giant covalent structure, and then you drop all the way to phosphorus, P4, which is a molecule, so that's going to go further down. And then S8 is about the same level as sodium, and then CO2 is even lower, and then argon is even lower. So there's CO2, that one is P4 as well as S8 molecule, and then sodium, magnesium, aluminium. So we're looking at magnesium, aluminium, we're looking at aluminium silicon, and we're looking at silicon phosphorus. In terms of that, so our melting point, the lowest one, definitely the lowest one will be your P4 molecule with a simple molecular structure, just breaking the weak van der Waals forces of attraction between the molecules. The highest one is definitely going to be silicon. As a result of your giant covalent structure, you have to break many strong covalent bonds in order to melt the silicon structure there. Okay, so we have a simple molecular structure or simple covalent structure just for the phosphorus there. So between magnesium and aluminium has a stronger metallic bond, so aluminium will have a slightly higher melting point than magnesium. So on our x-axis, phosphorus is the lowest, silicon is the highest. This one is okay. Phosphorus is the lowest, silicon is the highest, but we already crossed out option B based on the atomic radius. So we just need to have a look at this. Phosphorus is the smallest, well, lowest melting point. Silicon is the highest, that one is okay. Aluminium here, if you see aluminium here on the x-axis, it has the highest melting point. That one is definitely wrong. We are now left between A and C. We just have to compare magnesium and aluminium, I guess. Well, I should have seen it earlier actually. In terms of the atomic radii, we know that magnesium is bigger than aluminium. Magnesium is bigger than aluminium. Magnesium is above aluminium. Aluminium is not above magnesium. This is in terms of atomic radii. Aluminium is actually smaller than magnesium. A is not the answer. C must be the only correct answer as a result. I should probably draw a better straight line for this if I try to compare it. Okay. Question 16, we use chlorine in water treatment plants in order to kill microorganisms, harmful microorganisms. And this is a classic disproportionation of what just happened when you have chlorine dissolving in water. So it's not the disproportionation with sodium hydroxide, but it's just the disproportionation when you just dissolve in water, chlorine 0 as an element, then chlorine minus 1 in this hydrogen chloride or hydrochloric acid there. They're going to get chlorine plus 1 in the HClO, which is a molecule, so overall oxidation number is 0. Hydrogen is plus 1 in this compound, oxygen is minus 2 in a compound, so plus 1 for one hydrogen. Chlorine is what you want to find, minus 2 for one of the oxygen. Chlorine is plus 2 minus 1. Your calculator will not show you the plus, but you know better. Oxidation number has a sign and a value there, so A is the only correct answer there. Question 17, astatine is below iodine in group 7. So this is about prediction of the astatine chemistry. We know in terms of oxidizing power, oxidizing ability of the halogen. We talk about the halogen, the molecule X2, the diatomic molecule. F2 is more oxidizing than chlorine, than bromine, than iodine. And now you have astatine, which is a hypothetical unstable element on its own, but we're just thinking about the properties associated with its position in the periodic table. So we can expect this to be less oxidizing compared with the rest of the halogens. We also know that concentrated sulfuric acid lies somewhere in between the oxidizing power of chlorine and bromine, such that consulfuric acid will oxidize bromide to bromine, iodide to iodine, and consulfuric acid can therefore also oxidize astatite, At- minus to At0 in this molecule here. But it simply cannot oxidize chloride to chlorine or fluoride to fluorine because it's a weaker oxidizing agent than Cl2 than F2 here. So AgAt reacts with excess dilute aqueous ammonia to form a solution of a soluble complex. That is not going to be true because we know that AgCl, AgBr, and AgI, the solubility in aqueous ammonia will decrease because only the silver chloride dissolve in excess aqueous ammonia to give you a colorless solution. This cream precipitate only dissolve in excess concentrated ammonia, and this thing doesn't dissolve in ammonia at all, whether it's dilute or concentrated. So therefore, we expect the silver astatite to be even less soluble in aqueous ammonia, and you want a correct statement. Now in terms of astatine and KCl, so astatine as a molecule is a weaker oxidizing agent than Cl2, so you cannot oxidize Cl- to Cl2 because At2 is a weaker oxidizing agent or weaker oxidizing ability compared to chlorine there. Now Kat, basically the astatite ion, can react with dilute sulfuric acid, and in the first step not dilute sulfuric acid but consulfuric acid, but this one is dilute. So if you react with dilute, might or might not have a reaction, maybe no reaction because it has to be concentrated and not dilute. If we look at the last one, we have the astatite ion again, so it's the Na plus At minus, and this is consulfuric acid, and they will undergo a redox. That is possible because consulfuric acid is a stronger oxidizing agent than astatine. It can oxidize astatite to astatine. So your half equation astatite going to astatine can happen like that because corn sulfuric acid is a stronger oxidizing agent than your AT2 molecule. So therefore, D must be our only correct answer there. Question 18, we have more salt. This is a pale green crystalline solid, soluble in water. What is important is it has two cations, one of which is Fe2+, and the other one you don't know yet. So we have the missing cation, and that is our identity that we need to find. We heat it with aqueous sodium hydroxide. So we have to heat it, and we heat it only after we added some aqueous sodium hydroxide. We get a gas, we get a colorless gas, dissolved in water giving an alkaline solution. This is typical of ammonia gas. Why in the world do you get ammonia gas? Because you have ammonium ions, and when that react with any hydroxide, and when you heat it, you're going to get NH3 plus H2O, and it is this NH3 gas which is basic, which is alkaline, and it will turn red litmus paper, will turn blue. Okay, so that means you do not have ammonia, you have ammonium ion is present. Ammonium ion is present. That's why when you heat it with sodium hydroxide, you get NH3 there. Can also be thinking about this as a neutralization reaction because the NH4 plus is donating the proton. So this is the proton donor. This is the proton acceptor. So one of them is acting as a base and the other one is acting as an acid there. So the gas there is definitely NH3. And your cations, which is your green precipitate, that forms from the result of precipitation. You get a second reaction, which you can write an ionic equation, which must have the stat symbols. So the cation there will precipitate out with the hydroxide. And it's an iron 2 hydroxide. It's a dirty green precipitate. So FeOH twice solid. Balance equation, balance charges, and got to have the stat symbols in order to complete your ionic equation there. Question 19, this is thermal decomposition of an anhydrous calcium nitrate. Anhydrous means it is not hydrated, there is no water of crystallization. The first thing you should do really is write a balanced chemical equation. Group 2 nitrate decomposed to give you group 2 oxide. You also get nitrogen dioxide. This is a brown colored gas. I started with nitrate, 2 of them, so I get 2NO2. I also get oxygen gas, but immediately you can see 3 times 2 is 6 oxygen, 2 times 2 is 4 oxygen, plus 1 is 5 oxygen. 5 oxygen, I only need 1 oxygen, but I have oxygen molecule, so I must balance my equation with half of that. Now, having done all that, I want the mass of the solid residue. So I want the mass of these, and I know the mass of these. So to work out this thing, I will consider the idea of reacting masses from my O-level GCSE or IGCSE level chemistry. So work out the MR of the calcium nitrate first of all, and go straight to your periodic table. 40.1 for the calcium plus 2 times bracket, 14.0 plus 16.0 times 3 for the 3 oxygens, and I get 164.1. I just want to double check that I have already done the thing in the bracket correctly. 14.0 plus 16.0 times 3 give me 62, times 2 is 124, plus 40.1, I do get 164.1. Now the MR of the calcium oxide product, which is the solid residue there, we're going to get 40.1 plus 16.0, I get 56.1 there. Now I set up my mole ratio. So the mole ratio of calcium oxide is to the mole ratio of calcium nitrate. Hopefully you can see it's 1:1 from the balance equation. 1 mole of these give you 1 mole of calcium oxide. On the top there, I have the actual mole of calcium oxide. I want the mass of the calcium oxide that actually formed. Mass of MR, so that is the MR which I just calculated previously. At the bottom, I will also have the reacting mass, which is 4.10 gram divided by the MR, which it was 164.1. Now rearrange your equation and make the mass of calcium oxide the subject. So you get 4.10 divided by 164.1. You multiply by 1/1 is just itself, and then you bring up the 56.1 to the other side, and I get multiplied by that. So it's all about rearrangement of equations after you set up your mole ratio and mole calculation correctly. Okay, so 1.4016. So the closest one will be 1.40 gram to 3 significant figure. That's option C there. Question 20. So which reagent will give you a different observation with the two compounds P and Q? If I were you, I would always try and draw skeletal formula because I want to see what is happening. Okay, so I'm here HO, CH2, carbon from 4 bond, 1, 2. So there is 2 hydrogens. Carbon from 4 bond, there is only 1 hydrogen, there is 1 OH, and there's a CHO there, which is characteristic of an aldehyde structural formula. So I'll draw an aldehyde CH with CH there, carbon from 4 bond, 1, 2, 3. There is only 1 hydrogen. OH branch, CHO. We don't show the hydrogen bonded to the carbon there. So this is P there. What I can see is I have 2 different alcohols. So here I have a secondary alcohol because the carbon with the OH here, the carbon with the OH is bonded to 1 and 2 other carbon, secondary alcohol. On the other side, I have a primary alcohol because this carbon with the OH, the green carbon, the carbon with the OH is only bonded to 1 carbon. This is a primary alcohol. And last but not least, I have an aldehyde as well there. Okay. Now, after I've done all that, I should really try and draw Q as well. So Q is HO, CH2, and then a ketone. CO there is a ketone, CH2OH. Both of these are primary alcohol because the carbon with the OH is bonded only to 1 carbon, which is this central ketone here. So this is a ketone because it's a carbonyl without any hydrogen on either side. Instead, it's bonded to carbon and carbon there. In terms of different observations, so we have alcohol, we also have ketone versus aldehyde. In terms of bromine, so let's think about bromine chemistry. So bromine will react with alkene or alkynes, essentially unsaturated bond, well, unsaturated carbon there, which we don't have because both of them will be negative there. So you don't get any reaction for option A there because none of them contain alkene. Hot acidified KMnO4, this is a strong oxidizing agent. So you will get alcohol that can be oxidized, alcohol that can be oxidized. Yes, primary alcohol get oxidized all the way in this condition, which is extreme carboxylic acid. Secondary alcohol will be oxidized to ketone. The aldehyde can be oxidized to carboxylic acid, but both of them will undergo oxidation in the presence of that oxidizing agent. So it's not any different observation. Both of them will give you purple to colorless because the KMnO4 manganese plus 7, manganese plus 7 will go to manganese plus 2, which is your Mn2 plus aqueous, and that one is kind of pale pink, colorless. Silver nitrate in ammonia solution, that is basically Tollens reagent. As you know, Tollens reagent is used to test for aldehyde, so AgNH3 twice, plus, so this is a colorless solution, Tollens reagent C there. Tollens reagent will react with aldehyde, does not react with ketone, does not oxidize alcohol. C is definitely our answer. It's a different name for Tollens reagent, but if you know the underlying chemistry there, the silver plus 1, that is how you make Tollens reagent. Dissolve the silver. Am I correct? Well, usually we dissolve silver chloride and then we add excess ammonia to give us this. But you know, silver nitrate, a soluble source of silver plus 1, put it in ammonia, you're gonna get this complex as well. Warm acidified K2Cr2O7, this is dichromate. You can work out the oxidation number of this chromium, is plus 6. It's orange in color, and they will react with both of them, and you will get orange to green coloration. That goes from chromium plus 6, dichromate species, going to chromium plus 3, which is Cr3 plus, green color species. They will have oxidation for both of them there.